Hello guys, welcome to another video in the series of coding. Today we are going to do the problem which is called farthest number. So I are given an array of size n. For every element in the array, the task is to find the index of the farthest element in the array to the right, which is smaller than the current element. Let's try to take an example to understand this. Suppose this is the array. Let me write the indices of this array. 0, 1, 2, 3, 4, 5, 6, 7. First let's try to build the answer array which is expected out of us. So we have to return an answer array. Now for every element in this array, let's consider the first element. First element is 6, right? So for the element 6, you have to find the farthest element from 6 which is smaller than 6. Farthest element from 6 which is smaller than 6. Let's try to take example. So 6, consider the element 6. 2 is smaller than 6, 4 is smaller than 6, 3 is smaller than 6, 4 is smaller than 6, and 5 is smaller than 6. We have all these elements which are smaller than 6. Among all these elements, the farthest is this element 5, right? This is the farthest element and it is at the index of 7, right? It is at an index of 7. So we will store the answer 7. The farthest or the rightmost possible index is 7 because 5 is smaller than 6. It is satisfying the condition and it is also the farthest from 6, right? So we will store 7. Now let's go forward to the next element. Now there is no element smaller than 2 in this array which is to the right of 2. There is no element. So for this the answer is -1. Let's go to the next element. Next element is 4. Smaller than 4, we have only one element which is 3. Its index is 5. So our answer is 5. Let's go to the next element which is 8. Smaller than 8, we have the elements 3, 4 and 5. Among 3, 4 and 5, the farthest is 5, right? All of these are valid answers, but the farthest is 5. So we will store 7, which is the index, as our answer. Let's go to the next element which is 9. 3, 4 and 5, all the elements are smaller than 9, but the farthest is the element 5. So we will store its index which is 7. Let's go to the next element 3. There is nothing smaller than 3. So we will write -1. Similarly for 4, there is nothing smaller than 4. So we will write -1. Similarly for 5, it's -1. So this is our answer array. Now what we are doing is we are basically iterating for each element. We are taking each element for each element. Okay, how can we solve this problem using the brute force approach? Take each element. For each element, start iterating from right to left. Okay, for example, let's consider the first element 6. Okay, let's say we are at currently I equal to 0. I is the index, right? So first of all, we have to iterate through all elements. So I declare a for loop and I start iterating. So let's say first we are at I equal to 0 and the element I have is 6. Now let me start iterating from the right side. Okay, so I start my j from j equal to 7, then I shift my j to j equal to 6, j equal to 5 and so on, right? So I start another variable j. Now currently I am at j equal to 7. I notice that 5 is smaller than 6, right? 5 is smaller than 6. So I found my answer, because if I start iterating from right side, right? If I start from right to left, that means that whenever I find an element smaller, I have found my answer. As soon as I find an element smaller, right? See, if I start iterating from the right to left, whenever I find an element smaller, for example, I found 5 smaller than 6, so the index 7 is my answer. Okay, let's take another examples. Okay, let's take next example. In the next example, what happens is I is equal to 1, right? I is equal to 1, I see the element 2, right? So I start my iteration from j equal to 7. I check the element 5, compare it with 2. Now 5 is greater than 2, so this cannot be our answer. So I move my j pointer. Now j is equal to 6. Again I compare 4 and 2. 4 is also greater than 2, so it cannot be an answer. So I keep on shifting my j pointer till the end. I find no answer, right? So finally I say -1 as my answer. In the next iteration, I go to I equal to 2. I see the element 4. Okay, so I again start my iteration from j equal to 7. So I see the element 5. 5 is greater than 4, so this cannot be an answer. So I shift my j pointer, j equal to 6, 4 is equal to 4, again this cannot be the answer. So I go to the next element, j equal to 5. So now I see 3 is smaller than 4. As soon as I find an answer smaller, that means this is the farthest possible, because I am starting my iteration from the right side. Okay, so this is my answer. So I see the index 5 and I store the index 5 as our answer. Now the time complexity of this is O of n square, because first of all, for each element, right, for each element I am again iterating from right to left. So I am declaring 2 for loops, and the total time complexity is from O of n square. Okay, let's code this approach. So even this approach is going to work, but this is a brute force approach, even though it is getting accepted, but we can do this using a better solution. We will discuss that solution, but first let me code the brute force approach. So what we are doing, very simple thing, we are declaring 2 variables, and what we do is, whenever we find an element, right, if array of j, right, is less than array of I, that means we have found our answer. That's it, we can break, because we are starting the iteration from the right side. We start j from n minus 1. Okay, and we do this for all the elements. So let me declare a variable answer. By default answer is -1. So if we find an element which is smaller than the current element, that means that is our answer. We can just break. Okay, that's it. This is the simple code, and we are using 2 for loops. So the time complexity of this is O of n square. Now we have to return the answer vector. So let me write answer vector that we want to return, and here whenever we find answer, we are going to store answer for each of the elements, and finally we can return this answer vector. So this is the simple approach that we just discussed. Let me submit and see. So this is the brute force approach. It should work. So even though it's passing all the test cases, right, there is a better way to do this. Okay, so this is the brute force approach. Now from O of n square, can we improve the time complexity? So the expected time complexity for this problem is O of n log n. How can we bring to this time complexity? Let's discuss that. Okay, so we have this array. Now we are going to build a suffix array, right? What is a suffix array? Let's see what is a suffix array. So it's very simple. We are going to start iterating from right to left, and whenever we spot an element that is smaller than the current element, we are going to save it. Let's see it with an example. So let me write the suffix array. This is the suffix array. Okay, so these are our elements. Okay, so we are starting from the rightmost element. So currently in the suffix array we have only one element, which is 5. Okay, next we go to the next element we see 4. Now 4 is smaller than 5, right? Obviously 4 is smaller than 5. That means the smallest element we have seen till now is 4. So we will store 4 as our answer. Okay, so currently the answer was 5. Now we see 4 is smaller than 5. So in the suffix array corresponding to this, we will store 5. Now we see the next element, which is 3. Now 3 is smaller than 4, right? 3 is smaller than 4. So we will store 3. Now next we see 9. We will compare 9 and 3. Obviously now 9 is greater than 3. So the suffix array will continue as such. That means 3 was the smallest element we saw till now. We will continue and we will write 3 here. Next we spot 8. So we will compare 8 and 3. Now obviously 8 is greater than 3. That means we have not found a smaller element. The suffix array will continue as such. So 3 is the smallest element we have seen till now. We will continue. Next we compare 4 and 3. Again 4 is greater than 3. We have not found a smaller element. Obviously 3 is the smallest element till now. Okay. Next we compare 2 and 3. Now we have found a better element. 2 is less than 3. Okay. So 2 is the answer from this index onwards. Okay. Now we will compare 6 and 2. Now 6 is greater than 2. So we will continue with 2 itself. So suffix array basically stores the smallest element, okay, the smallest element we have seen till now when we are iterating from right to left. Okay, smallest element at each step we are going to store that. Now how is the suffix array useful? Let's see that. So let's start with the very first element. Okay, we are starting with the very first element to find out our answer. Okay, this is the answer that we have to build. Okay, let's see how this suffix array is very useful to get our answer, that too in the best possible time complexity. Now we are going to use this suffix array to find our answer. in the best time complexity. Let's see how we can do that. So we have to build this answer array, right? So for each element we have to build it. Let's start from the first element. So let's start from I equal to 0. The element is 6, right? For this we have to find the farthest element from 6, which is just smaller than 6. Any element smaller than 6 is okay, but we need to find the farthest such element. Okay? So let's start. So now we have the suffix array. That means we have the list of elements which are smaller than 6, right? So we have this suffix array. We have the element 6. Okay? We are going to apply binary search on this suffix array to try to see the farthest element which is smaller than 6. Okay? Let's start. So we have a low and we have a high and we have a mid in binary search. Okay? Now the mid is currently 3. We are going to compare our element with the mid value. So we see that 3 is smaller than 6, right? That means we have found the element smaller. We need to find the farthest element smaller than 6. We see 3 is less than 6. That means we have found the element smaller than 6 at least. Now in the suffix array, we have stored the elements in such a order that if they are always going to be in this order, right? I mean, they are always going to be sorted in increasing order in this side. Okay? Because suffix array we have stored in that order only, that the smallest element is on the left side and the largest element will be on the right side, right? So this is a sorted array and you can apply binary search on a sorted array, right? So now we have found 3 is less than 6. We need to find farthest such elements, right? So we have to try to find the answer in the right side. Now once we know that 3 is smaller than 6 and 3 is at an index of 4, right? The current index is 4, right? This is the index. These are the index values. So in the answer at least we will store 4. At least the index 4 is our answer. Okay? Actual answer is 7. We will reach to that, but at least we know that at the 4th index we have an element 3 which is smaller than 6. Okay? At least we have this in our hand. So we can reduce the search space in only this much portion. We need to find if we can get a better answer for 6, if we can get a even farther element, right? At least we know that 3 is our answer. Let's try to get an even farther element, but we need not even look in the search space. From binary search we are eliminating looking this side. We need not even look in this search space, because once you know at least 3 is less than 6, we can try a better answer in the right side. In the left side we need not even try the answers, because any answer will be even less farther, right? On the left side any answer will be even less farther, right? We don't want less farther answers. We want answers which are more farther. We want to find the farthest possible element that you can get only from the right side. Okay? So once we have found the answer, what we will do is we will store the answer. Currently the answer is equal to 4, and what we will do, we will reduce the search space. Now in the next iterations we will again change our values. So for the next iteration, only this portion is our low, this portion is our high, this portion is our mid, this entire search space is gone. Okay, this is what is the logic of binary search. Okay, now let's continue forward. Currently we are storing the answer as 4. Let's continue. Now we see the element 4 and the current element is 6, right? At the mid we see the element 4. Again we see 4 is less than 6. Okay, so very good. Again we have found answer. So the farthest possible is 6 till now. So since 4 is less than 6, 4 is at an index of 6. Okay, so we will change our answer and our answer will become equal to 6. Again this search space can be reduced and we will be left with only the remaining search space. Okay, so let me change the search space. So now again we will change the search space. This search space was already eliminated, this is again eliminated. Now we have to search only within this search space. Low is equal to low, high, mid, everything will come at 5. Again we will compare 5 and 6. 5 is again less than 6, right? The current element 5 is again less than 6. So that means that this is our farthest possible answer. Okay, so the answer will become equal to 7. So we have reached the answer 7, which is what we wanted. Now next time what will happen, again when you try going to the right side you will change low. Now low will become greater than high, so we can exit from the loop. Okay, so that's it. We have found the answer for each element. For each element we will do this, right? So we are going to iterate n times for each element, and binary search complexity is just log n. So in n log n we'll be able to find. Now let's move forward to coding it. So in the first case we have to declare a suffix array. So let's declare the suffix array. It's also going to be of length n. Now we're going to start iterating from the right side. So let's take an example. Let's say we have 3, 4, 2, 6 in our as our array. To build the suffix array, first of all, let's say we have to build the suffix array. So the last element of the suffix array will be same as the current element. So we can simply give suffix of n minus 1 is the same as array of n minus 1, because there is nothing on the right side to compare, right? Now let's see the next element. From the next elements onwards from the right side, so first we will iterate from the right side. So I equal to n minus 2 to I equal to 0, I minus minus, because we are coming from right to left. Now we are going to compare this element. We are going to compare 2 and 6, right? So first of all, let's compare. So if array of I is less than suffix of I plus 1, that means we are comparing 2 with 6. Now in our example, 2 is less than 6, right? So in the suffix array we are going to store 2 here. Okay, at this position the smallest element is 2, so 2 is going to be our answer. So suffix of I will be equal to array of I. Else, if this condition is not true, let's see the next element. Next time we are going to compare 4 with 2. Now 4 is greater than 2, right? So we are going to continue with 2. So for the even for the next element, 3 is greater than 2, right? So the smallest element is 2, so we are going to continue with 2. So in all these cases we will reach the else condition where we are going to continue with the answer. So suffix of I will be equal to suffix of I plus 1. So this is how we are going to build the suffix array. Now once we have built the suffix array, now it's simple. We have to just apply binary search on each element, right? So first of all, on each element, so we are going to iterate for int I equal to 0, I less than n, I plus plus. We are going to apply the binary search. So low is going to be I plus 1, just the next element from the current element, and high is going to be the last element, right? Now we are going to apply the binary search. So what is the condition for binary search? Low should be less than equal to high. And what is the mid value in the binary search? The mid value is always the low plus high value by 2. Okay. What are we comparing? We are comparing if the value at the mid position, right? If suffix of mid is less than array of I, if this is the condition, that means it's great. We have reached at least one answer. So by default, initially we can give answer equal to minus 1. Whenever we find an answer will be the index. So answer is the mid value. But we can find a better answer. We can still look for a better answer. We can still look for a better answer on the left side. Sorry, on the right side. Why we can look for a better answer on the right side? Because it is sorted in increasing order. And on the right side we have all elements, right? Which are greater than the current element, but they are also farthest, right? They are also farthest. On the right side we will find the farthest elements, right? So whenever we find an element that is still smaller than our current element and it's on the right side, it's even better for us, right? It's even advantageous because we need to find the farthest possible answer. So where will we look for? Once we have found the answers, we'll try to look on the right side, because right side will give us the farthest possible answers. So we can still try to look for a better answer on the right side. How can we do that? Low can be incremented by mid plus 1. That's how we go on the right side. Otherwise we can go on the left side and try to look for a answer. If we enter into the else condition, that is the value at the mid, if that is going to be greater than the current element, that means on the right side we can never find an answer, and we have still not found an answer. Let's try to look for an answer on the left side. So that's a possibility of finding the answer. So finally we will find the answer. And now let me declare a vector int answer that we are going to finally return, and we can push back answer dot push back answer, and we can finally return answer. Okay, so let me submit and see if this is working. Is also working. Thank you for being patient and listening. Hey guys, a short 1-minute break. Lot of you keep asking about what courses should I take to prepare for placements. I would like to share the course that I had taken during my placements, which was from GeeksforGeeks. Their data structures and algorithms course was what I had taken, which is this course, DSL Live for working professionals, and it was very helpful. In fact, one of the questions that was discussed during the class, that was actually asked in the second round of my interview with Microsoft, and it was very helpful course for building the concepts, and they had discussed a lot of interview problems during the class, so it gave me a lot of confidence during my placements, and the course was extremely helpful. The pace of the course was very nice. They started from the basics, from every topic. They covered every topic from arrays to dynamic programming to graphs. All of the topics were covered in detail, and the instructor was also very nice. The instructor was very helpful, and he cleared all the doubts that we had during classes. And I had taken live classes because I found it very helpful to maintain discipline. That's why I had taken live classes. But I have taken their other courses also. I have taken their system design course also, which is very helpful. So these are all of the courses. I will put the link in description. You can check it out. And there is one amazing news, that if you want a discount on their courses, then you can use coupon code Alicia on any of their courses, and you will get a 10% discount, which is pretty amazing. So do check out their courses. Thank you.